All right. Happy Monday, I guess. So let's see. We left off last Friday talking about this example of thermal resistances. So we will continue on this discussion of thermal resistances today, kind of wrapping up. We're slightly behind in our lectures already, but that's fine. We'll catch up. So we'll finish talking about thermal resistances, and then we'll go into an example on how you might use thermal resistances when it's not entirely clear that it's valid. So we'll do that. Before we get started, just a couple reminders, I guess. Homework 1 is due Friday. That's been posted. It's on Canvas. Should probably have had a look at that. We should get through the material needed to do it today. So that shouldn't be a problem. Let's see, I wanted to ask about office hours. I had scheduled them from 12 to 1 on Wednesday and 12:30 to 1:30 on Thursdays as was in the syllabus. Just think for a second about your schedule, whether that works. So I want to know if those two times don't work for you. So if neither of those work for you, just could you raise your hand? Okay, perfect. So theoretically, if you have questions, everybody should be okay to come to office hours. If for some reason you have a more substantial issue that you probably don't feel could be addressed in office hours, I can always schedule something separately. We can talk, but obviously prefer to come to office hours if you can. All right, good. So let's get started on the actual stuff here. Again, so we left off here with this example, and remember what we were doing was we were trying to look at this problem. We have two known temperatures, TH and TC, and we were trying to just, with our knowledge of the conductivity, be able to sketch a profile. All right, so we came up and we said the conductivity A is higher than B, so we know that the resistance from A to B, from 0 to L has to be lower, and the temperature drop has to be lower to go with that. All right, so let's modify this example just a little bit and introduce another resistance idea. So let's say at this interface here between A and B, it's two different materials, so you have maybe two blocks that are clamped together. And when you have that situation, you might have, if you were to blow this up, you look at a blown up version of this, the interface might actually look like this at the micro scale, right? You've got these points where you have sort of incomplete contact between the two media. Right, and if that is the case, then you have maybe an air gap or whatever. If these are, say, immersed in oil or something, there's some other substance that's coming between the conducting bodies. And that introduces something called a contact resistance. Okay, so contact resistance, that's normally given to you as a coefficient. And so somebody might say, okay, my R double prime C is some value. And we would convert that to a resistance, an actual thermal resistance, by taking that coefficient and dividing by area. So we'd say RC, the actual contact resistance, which has units of Kelvin per watt, is going to be equal to R double prime C divided by the area in contact, A sub AC. All right, so that means that the units on this R double prime C must be what? Kelvin meters squared per watt. And so you always want to remember, I guess the tricky part is remember to divide instead of multiply. So you have this double prime, you think maybe I should be multiplying by, you always want to divide by that. So how do you get that the R double prime C? Usually that's something that you get through empirical data, or you have a lookup or some kind of table that says I've got these two materials. There's this pressure between the materials. There's this substance between it, air, oil, whatever you have. And you'll get that contact resistance. So that's normally an experimental value. All right, let's draw then how this temperature profile might change if we introduce a thermal resistance due to contact. So let me just, I'll use my existing plot below. So let's see. So if I were to draw the temperature profile on this existing plot, I'm introducing another resistance, which means I'm introducing another temperature drop at this interface here. All right, so the total resistance from here to here, if these two stay the same, is going to go up. All right, that means the heat flow is going down, which means that the temperature drop that I had for this one, this original one, actually has to be slightly less because I have less heat flowing, right? So if I'm going to draw this this new plot, I'll draw it in red. It might look something like this. Right? I've got slightly less temperature drop. Now I have a contact resistance at this point, and that contact resistance exists over what looks to us like an infinitely small distance. So you're going to have essentially a vertical line, right? A vertical line here due to that contact resistance. And then we're holding this side, this temperature constant over here, so the remainder just has to be what's left, like this. All right, so this whole thing is driven by this contact resistance. All right. There's another thermal resistance that's very similar to this, but involves a fouling of a surface. So let's say I have, I don't know, just sketch out an idea here. So we have maybe some cylinder, and I have fluid flowing through that cylinder, and I want to measure the thermal resistance as heat is going out of that cylinder, right? I've got some hot, maybe air going through it, and that's rejecting heat outward. Over time, you're going to start getting accumulation of debris or some, precipitants on the surface, on the internal surface, where the air is flowing through here, right? So you might get this kind of thin layer that builds up on the inside of a tube. Any real industrial process is going to have this because you have impurities in the substance. As that builds up, it introduces an additional thermal resistance. And that can be a significant thing, right? It can actually change the temperatures in the system. So this is called fouling resistance. And fouling resistance is, again, kind of the same idea, or the same mathematically, the same idea, which is R double prime F. And we would model the actual resistance as RF equals R double prime F over AC, or AC, or maybe AC is the wrong term, but it's the surface area that's exposed, right? It's the diameter times pi of that internal tube. All right, so these two are resistances that are introduced at kind of a discrete location, right? And you see an immediate temperature drop due to those. Any questions on that? Okay, pretty straightforward. All right, so I said you would get these types of things in a table. Just zoom in here, maybe not. There we go. So this would be for contact resistance. You'd say I've got these two materials. I have stainless on A and aluminum on B, and I know that the surface roughness is roughly 1.2 micron. They're in air. They're at this temperature. So this is the value that you would then put into that specific resistance. So again, these are things that you'd have to look up. A lot of times you might go through the analysis and just try to convince yourself that these are not important. So you could look at whether the magnitude is a roughly order of magnitude actually even matters in your problem, and we'll look at an example for that. But you would need to go to something like this to get those values. Okay, so just to recap, I guess, where we stand, we've now gone through a bunch of different resistance formula, and the idea is that we now have this, what we call like a toolbox, or just a conceptual toolbox for how you're going to approach heat transfer problems. Every time you sit down, you need to figure out, okay, do I need to model this as a 1D problem? Do I need to model it as a 2D or 3D problem? Do I need to include conduction? Do I need to include convection? Or you don't want to spend your entire career sitting there doing stuff you don't have to do just because you don't know what's important. So this toolbox is, from a heat transfer perspective, the best way to make a quick assessment about whether or not what you're doing is worthwhile. Right? It's an easy step that you can take to be lazy, basically. All right? So we have our conduction resistances, we have our radiation, the exact representation, radiation, approximate. Contact, I didn't put following in here, but it's the same idea, right? So you're going to want to use this and keep this kind of thing handy for what you're doing.